Welcome to linear second order ODEs in theory. So quick just definition, what is a linear second order differential equation? A second order differential equation is said to be linear if it can be written in the form y double prime plus some function p of x times y prime plus a function q of x times y is equal to f of x. This looks fairly similar to the linear first order differential equations. It's just that we now have a second order derivative included, and any of the other order derivatives can be multiplied by a function of x. That function on the right is often referred to as the forcing function. The reason for this is in physics equations, external forces typically appear on the right-hand side. All right, so if we consider a linear second order differential equation, just like with first order, we can have homogeneous and non-homogeneous equations. So a linear second order differential equation is said to be homogeneous if that forcing function, so the forcing function f of x is identically 0. So in other words, we have y double prime plus p of x times y prime plus q of x times y is equal to 0. So it's essentially the same definition as in the first order case. Similarly, a linear second order differential equation is said to be non-homogeneous if f of x is not identically 0. So a linear second order differential equation is said to be non-homogeneous if f of x is not identically 0. So this is just our generic y double prime plus p of x y prime plus q of x y equals f of x. Just like with first order linear differential equations, the homogeneous equations are a little simpler to solve, and then we need additional work to find the non-homogeneous solutions. From here, we're going to move on to the existence and uniqueness theorem, and this is going to be for homogeneous linear second order equations. So let's go ahead and consider the IVP. given by y double prime plus p of x times y prime plus q of x times y is equal to 0, with initial conditions y of x naught is equal to, your textbook does k1 and k2, so y of x naught is equal to some constant k1, and y prime of x naught is equal to some k2, where k1 and k2 are both real numbers. If p, q, or p and q, so if p and q are both continuous, on open interval AB, containing x naught, then there exists a unique solution to the IVP on interval AB. So again, this is just like the theorem we had before. Now we just need both of those functions before y prime and before y to be continuous on the interval. Again, so far this theorem, we're only looking at homogeneous equations.